Okay, so today we're going to do a few problems looking at applications of Gauss's law to actually find the electric field due to some simple configurations of charge. These are all examples from your textbook, but we're going to go over the three, I think, most important and most commonly seen applications of Gauss's law. The first one is looking at the electric field of an infinite line of charge. And we actually did this already in chapter 21 by directly integrating the electric field dE at some point in space due to an infinite line of charge. And you can go back and look at that example and watch that video again if you don't remember doing that calculation. But here's example 22-6. It says we've got a long uniform line of charge, and by long we can assume that that means that if you're close enough to it, it's as if it extends from plus infinity to minus infinity. And it possesses a uniform positive charge with a charge per unit length of lambda. So lambda is the charge per unit length of this line. Calculate the electric field at points near the wire but outside the wire, so some distance away from the wire that they're calling R, far from the ends, which is another way of saying you can treat the wire as being infinitely long. You don't have to worry about what we sometimes call in physics edge effects. You can assume that this wire extends indefinitely along the positive and negative axes. I'm actually going to change the arrangement of this from the way that your book sets it up. And the reason for that is one of the reasons for spending so much time learning how to work in the curvilinear coordinate systems like spherical and cylindrical coordinates is for solving just this sort of problem. So instead of setting up the problem with the line of charge horizontally, I'm going to put that line along the, maybe I'll use the drawing tools to actually make a straight line, okay, like this. Okay. So here's my line of charge, and let's say that it extends indefinitely up the plus and minus z axis. So we are in cylindrical coordinates right now. Let's remind ourselves what Gauss's law says. Gauss's law says if you take the electric field and you integrate it over a closed surface, the integral of E, which is a vector, dot dA, which is a vector, and this dot product takes care of only measuring the flux through the surface, perpendicular through the surface, and by definition, this integral for Gauss's law is over a closed surface. That is equal to the charge enclosed in your surface divided by epsilon 0. And we said last time we were talking about Gauss's law that this integral is, in general, really complicated because you can't be guaranteed that for any particular electric field that the electric field vector and the area vector are perpendicular to one another. You also can't be guaranteed that the electric field is constant everywhere on that surface unless you choose the surface specifically so that those conditions are met. So when doing a problem involving Gauss's law, what you want to do is you want to look at the symmetry of the situation. And you want to ask yourself what kind of surface is the right surface to choose to integrate over in order to use Gauss's law. So here we've got our line charge with density lambda, positive charge density per unit length. And if we ask ourselves, when we go out here, what is the electric field going to look like? We already said when we integrated directly to find this electric field that we know the electric field has to be away from the line and cannot have any component in this direction, in the up and down direction, because for every little bit of the line above this point, there's a equivalent amount of charge below that point pushing the opposite direction. So any component in this direction cancels out, leaving only the force in this direction. We can also see from the symmetry of this problem that the electric field at some point in space can't depend on theta because a line of charge looks the same no matter what direction you look at it from. So there can't be any dependence on the electric field on theta. And also, if this line is infinitely long, there can't be any dependence on how far up and down the line you are, because an infinitely long line looks the same no matter how far up or down the line we know. So what we know from this is that the electric field is going to be just a function of rho the radial coordinate in cylindrical coordinates, and we know it's going to be in the rho hat direction. We know the electric field has to be in this direction, and the only thing it can depend on is the distance from the line. So, what is the right shape to draw in order to capture this electric field and this relationship between the electric field and the direction vectors? Well, if the electric field is always radially out from the line, we want to choose a surface whose normal will always be perpendicular to that electric field. And hopefully it's fairly clear that this, maybe I should use a different color, that the surface that we should choose is a cylinder of radius r that surrounds, this is going to be hard to draw on a tablet, okay, that surrounds the line so that every point on the cylinder is the same distance, let's call it r, away from the line. If that's true, since E is only a function of that radial distance, the electric field will be the same everywhere on this outer surface of the cylinder. Now, Gauss's law demands that this surface be a closed surface, so our surface also has to include the top and bottom of the cylinder. But that's okay, because we know that the electric field is radially out this way. On this top and bottom surface, we know that E dot dA, where A is the normal to the surface, is going to be equal to 0, because the surface normal of those caps of the cylinder are this way, and the electric field is that way. And there's no flux through that surface because the electric field only goes radially outward. Okay, so we're going to choose as our surface what we sometimes call our Gaussian surface, a cylinder of radius r that surrounds, oops, I erased too much, that surrounds our line. And I just want to clean this up a little bit before we get started. Okay, so there's our, ooh, I came back. Uh-oh, I froze in OneNote with all my erasing. Hold on a second. Let me open that back up again. Okay, so let's say that our cylinder has a radius of r and a height of, it doesn't matter what we call the height, let's call it L, capital L. So Gauss's law tells us that if we integrate the electric field over this surface, the integral of E dot dA is equal to the enclosed charge divided by epsilon naught. How much charge is enclosed by our cylinder? It's just the amount of charge on the part of the line that's inside our cylinder. So the enclosed charge is equal to lambda, the charge density, times L, the height of our cylinder, divided by epsilon 0. The integral of the electric field over the area, we should actually, if we're being really, really explicit, we would write that as three separate parts. It's the integral of E dot dA over the round top of the cylinder, plus the integral of E dot dA over the outer boundary of the cylinder, plus the integral of E dot dA over the round bottom of the cylinder. But we know from the symmetry of the problem that the integral of E dot dA here is 0 because the dot product of E and A is 0. The area vector is this way, the electric field is this way, so that goes away. And we know the same thing about the bottom, that the integral of E dot dA over that bottom surface is going to be 0. So the only remaining electric field left is the integral of E dot dA over the cylindrical outer surface. Write that a little bit more clearly. So this is the integral of E dot dA over over, I'll just put an arrow over that surface, is equal to the charge density times the length, that's the enclosed charge, divided by epsilon 0. We already said that symmetry considerations tell us that the electric field is only a function of the distance from the line. And so since the whole surface of the cylinder is the same distance away from the line, that means the electric field is constant over the area, and we can just pull that electric field outside of the integral. So we've got the integral of E times the integral of dA is equal to lambda L over epsilon 0. And the integral of dA over the surface of the cylinder is just the area of the cylinder. We don't even need to integrate anything because the electric field is constant. That's why we chose that particular surface. So the area of that cylindrical wrap is 2 pi r, the circumference of the cylinder, times L. You can think of a cylinder as an unrolled rectangle. That part of the cylinder is unrolling into a rectangle that has one side 2 pi r and the other side L. So what we've got is E times 2 pi r L is equal to the charge density times the length of the cylinder over epsilon 0. Notice that the L's cancel. They have to cancel because the L has no physical significance in our problem. The L is just a height of an arbitrary cylinder that we made up in space. It can't enter into the problem because it doesn't have any physical reality. It's just a made-up surface that we generated. So thank goodness it cancels out and we can get rid of it. And this leaves behind that the electric field is equal to, what have we got left? We've got 1 over 2 pi epsilon naught lambda over r. So the electric field is radially outward. If we want to put the direction in here, we can add a rho hat in cylindrical coordinates. The electric field is radially outward and it falls off inversely with the distance. It's proportional to 1 over r. And we talked about that result when we did the direct integration. If you go back and look at that problem, you should find that that's the same answer that we got. So this was a much easier integral to do. In fact, there was no integrating to be done. All we need to do is to know the area of a cylinder. So what we see is that Gauss's law can give us an answer for what is the electric field in space if we have a situation that is so symmetrical that we can choose a surface on which E is perpendicular and constant. As you might guess, there's only a small number of physical shapes that you can think of where this is a useful approach. So what we'll see is that there are 2 or 3 more examples we can do of using Gauss's law to actually find the electric field in a simple situation. Other applications of Gauss's law in more complicated situations are beyond the scope of this class, and you will see them again if you go on to study physics in your sort of 2nd and 3rd year electromagnetism courses. So let me stop there, take a little break, and then we'll come back and we'll do the electric field of some other shapes using Gauss's law.